Example 4.3.1, resistivity and temperature coefficient of resistance. The question is a 14 volt DC voltage source is connected to a 250 ohm load via 100 meters of 2.5 millimeter square copper wire. Assuming that the resistivity of copper at 20 degrees C is 1.728 times 1.72 times 10 to the minus 8 ohm meters, and copper has a temperature coefficient of resistance of 0.004 per degrees Celsius, find the voltage delivered to the load at 2040 C. So let's start the problem by writing the givens. We've got a DC voltage source that in the problem statement was given to us as 14 volts DC. We have a load resistance, we'll call that R sub L, it's 250 ohms. We have some wire, and we know that the length of that wire is 100 meters. We know that the cross-sectional area of that wire, the circular cross-section, is 2.5 square millimeters. The next parameter we're given is resistivity. That's the symbol rho. Here I'm writing resistivity, trying to write resistivity sub Cu, Cu being the chemical symbol for copper. So that's 1.72 e to the minus 8th ohm meters. Remember, that's resistivity is ohms times meters. And that was measured at 20 degrees C. The resistivity of materials is actually temperature dependent. The factor that tells you how resistivity changes with temperature is the temperature coefficient of resistance of a material, alpha. So alpha of copper is 0.004 per degrees C. We need to answer this question twice. We need to find what the load voltage is under two different operating conditions. One is temperature, one is 20 degrees C, which is considered room temperature for most standard applications. And then T2 is 40 degrees C. What happens when our ambient temperature gets a little bit warmer? So there we have all the givens for the problem. Hopefully you were able to extract that. That's really just making sure you understood what was explained in the chapter where those different variables come from. So now let's get to writing the solution. First thing we're going to do is start by creating a circuit diagram. We want to, kind of, what does this circuit look like? What's the topology? What's the known values, etc. So this is a single phase DC circuit. So there's a wire that connects the source to the load. So that's our line, how much resistance the wire has. Here's the load. And then in single phase DC circuits, we have to have a return that current flows through. So that wire also has a resistance associated with it. So here's our circuit model for a single phase DC. So we need to figure out what our line is. Since it's 100 meters to and 100 meters from the load, those are going to be equal. So our line 1, the resistance of the line going to the load is going to be the same in this situation. That's not always the case. It is for this. Remember, we don't do that in three-phase because the currents don't flow in balance three-phase. They cancel out the neutral, so you don't include the effects of the return current in three-phase. But in single-phase systems, you have to. You get that additional voltage drop across the conductor that connects back to the load because there is current flow through it. It's not true in three-phase. So if you notice, we didn't do this in three-phase systems. That's why. We assume balanced operation. So anyway, what we need to do next is calculate the resistance of that line. That's rho times L over A, or resistivity times length divided by cross-sectional area. So that information was given to us in the problem statement. We wrote it up above at 20 degrees Celsius. So we need to multiply the resistivity of copper, rho, 1.72 times 10 to the minus 8 ohm meters. We then need to multiply by the length of the line, which was 100 meters. And then we have to multiply by cross-sectional area, 2.5 millimeters squared. You'll notice immediately that we've got a dimension problem here. We need to cancel out our units. We've got millimeters and then denominator, and we got meters in the numerator. It's a little tricky because we got millimeters squared in the denominator, so that's actually millimeter time millimeter. So if we want to cancel that out, we have to put in a cross multiplier twice to get rid of that millimeter squared. So there's 1,000 millimeters for every meter. So it'll cancel out one of the millimeters right there, and I got to do it a second time. We'll just put the squared term up there in the numerator. So do that math out, you can see that we'll cancel out the millimeters from the numerator and the denominator. That'll just leave you with ohms. 0.688 ohms is the total lumped resistance of that line, 100 meters of line, and that's measured at 20 degrees C, because that's the temperature that the resistivity coefficient was given at. So R20 is equal to 0.688. So now I'll just redraw the circuit, filling in the appropriate values. We got 14 volts. There's the 2 times 0.688. I'm lumping the two resistances together here. You can do that in a series circuit. And so you can see the way that I'm going to approach solving this is that this is a voltage divider circuit. So load times source divided by total series resistance is going to give me the voltage dropped across the load. So that's going to be V load measured across that 250 ohm resistor. It's going to be found by 14 volts, the source voltage, times the load voltage, 250 ohms, divided by our total, which is just the series, which is 250 plus 2 times 0.688. So 14 times 250 over 2 times 0.688 plus 250. And I'm going to get a load voltage of 13.9234 volts. So that's the voltage delivered to the load if the air temperature was 20 degrees Celsius, or the temperature of the wire was 20 degrees Celsius. Second part of the problem asked us to determine the same voltage if the temperature of the wire increased from 20 C to 40 C. So we could solve that by looking up the temperature resistivity of copper at 40 degrees C in a table. If we had a table that was detailed, that's not usually typical. Instead, what we'll do is we use a rating factor. The line resistance at 40 degrees C is going to be the 20 degrees measured temperature times 1 plus whatever the temperature coefficient of resistance is times the temperature change, the increase in temperature. So our old values were the values measured in part A for 20 degrees Celsius. So we get 0.688 for the resistance. That was the original one. It's 1 plus alpha, which was 0.004 per degree C. And then the temperature difference is going to be our new temperature, 40 degrees, minus our old temperature, which is the temperature that we calculated previously, 20 degrees Celsius. You can see there that in this formula, the C's cancel out. And so you end up with a increase in resistance from 0.688 up to 0.74304 ohms. So now all we have to do is repeat that voltage divider formula. The load resistance stays the same. It's not temperature dependent. What changed was the resistance of the line, the interconnect, that line there. And so we just need to redo that voltage divider with those new values. So it's 14 volts, 250 ohms, and then we just change the denominator. It's going to be 2 times 0.74304 plus 250. Again, that's just that voltage divider formula. So this time you're going to get a 13.9173. So you can see what the effect was the increase of 20 degrees C with the same wire interconnect caused the load voltage to decrease from 13.9234 to 13.9173. And that's because of the increase in resistance of the wire that connects the source to the load. So that is generally true of all systems, is that the resistance will tend to increase with temperature. And so that 14 volts gets split amongst the two different resistors in our circuit model there, resulting in a decreasing load voltage as we see increasing ambient temperatures. So real effect in power systems. I know we did it for DC, it's because it's a little bit simpler, but this is a real effect in AC power systems. The voltage delivered to loads, if uncompensated, will decrease as the temperature of the conductors increases in the system.